We all know the hydrological cycle illustrated here. In this lesson, we will discuss more in depth the formation of rain by starting to recall some basic thermodynamics. As illustrated here, water is present in our ecosystem under three possible forms: liquid water, vapor, and ice. If we consider water vapor as an ideal gas, these laws apply, where the temperature T is expressed in the Kelvin scale, where small p is the pressure in pascals and V is the volume. This law here describes an isothermal process. The product of pressure and volume is constant if the temperature is constant. Then, if the temperature changes, the pressure varies according to this expression for a constant volume here, and we have a similar expression for the variation of volume if the pressure remains constant. This leads to the ideal gas expression that can be transformed like this for a constant mass of gas. According to Dalton's law, when ideal gases are mixed in a given volume, the resulting pressure is the sum of the individual pressures if each gas was alone in this volume. Then, finally, we have this relation here for adiabatic compression or expansions, where the exponent gamma is equal to 1.4 for air. Just to remind you, an adiabatic process is a process occurring without heat exchange. To explain the formation of rain, a key concept is that of vapor pressure that can be highlighted by this experiment. A tube filled with mercury is put upside down over a container also filled with mercury. Mercury in the tube will be at equilibrium at a height of 760 mm, highlighting the effect of the atmospheric pressure. Indeed, writing the piezometric head here at points A, here at the top of the column, and at point B over the container, and considering that the pressure at point A is 0 because we have void, the atmospheric pressure is expressed as a function of the height of the column of mercury. Now, if we add 1 drop of water to the upper part of the column, this water transforms into vapor because of the very low pressure, and as a consequence, the level of mercury here decreases by delta H. And the new equilibrium can be written like this here, where we see that the pressure at point A is not 0 anymore. If we continue adding water, delta H will increase up to a certain value when no more liquid water can be transformed into vapor. The water vapor is said to be saturated, and the corresponding pressure PA is the saturated vapor pressure. The saturated vapor pressure evolves with temperature. One well-known value is at 100 degrees on the Celsius scale, when water boils at atmospheric pressure. The corresponding point is indicated here in green. Some intermediate values are given in the table, the pressure being expressed here in millimeters of mercury. From this table, it is possible to calculate the specific mass of water at different temperatures using the ideal gas law recalled here in equation 1. Let's consider that we have a given constant mass of water m. This mass is the same at temperature T1 and T2, so that we can write equation 2 with different volumes because of the different temperatures. From equations 1 and 2, we can write the ratio V1 over V2, that is here. If we now consider that state 1 from this equation corresponds to the temperature of 0 degree in the Celsius scale, that is 273.15 in the Kelvin scale, and knowing that at atmospheric pressure the specific mass of water vapor is 804 grams per cubic meter, we can determine the specific mass of water vapor at saturated pressure at different temperatures. The results of equation 3 are indicated in the table here. We can see that at 20 degrees, for example, the mass of water under the form of vapor is more than 3 times the same mass at 0 degrees. For temperatures below 0 degrees, the curve giving the transition between vapor and ice is actually double, the curve that is here highlighted. The red curve indicates a transition between vapor and supercooled water. This supercooled water is water that remains liquid although the temperature is below 0 degrees. This can happen when no impurity, no small dust particles exist around which crystallization could start. The variation of specific mass of water with temperature explains the key mechanism of rain formation, that is condensation. For example, if the temperature decreases, less water can be present under the form of vapor in a given volume of air, and the excess water becomes liquid. Condensation can also occur from the mixing of two masses of air at different temperatures. Let us consider the masses of air A and B at two different temperatures. When mixed, the resulting representative point is M, and we see that this point M is on the liquid side, while A and B were on the vapor side. So this means that part of the water that is present will condensate. Let's illustrate this by means of an example. Consider that we mix 1 cubic meter of gas at 10 degrees here, containing 9 grams of water, with 1 cubic meter of gas at 30 degrees, containing 29 grams of water. We see that these two values are below the values of the limit vapor pressure that we see here. We have 9 instead of 9.33, and we have 29 that is below 30. So these two masses are indeed present, these two masses of water are indeed present under the form of vapor. When we mix them, we obtain 2 cubic meters of water at 20 degrees, containing 38 grams of water. So this means, in fact, a specific mass of 19 grams per cubic meter. This value for 20 degrees, if we look here, is now above the limit, and it means that we will have 2 grams approximately of water that will condensate. So we can summarize the 3 mechanisms leading to condensation. First, a simple temperature decrease. Secondly, the mixing of 2 masses of air at different temperatures. And the third mechanism is expansion. This is maybe less obvious, as a simple isothermal expression would lead to liquid water becoming vapor and not the opposite. But in the reality, such an isothermal expansion is impossible in the atmosphere, as it would require heat transfer between huge air masses very distant from each other. So expansion in the atmosphere is in fact an adiabatic process. No heat exchanges occur, and as a result, the temperature decreases with the decrease of pressure. So water vapor can become liquid if the pressure decreases, for example, in altitude. Talking about altitude, we can ask ourselves, how do temperatures evolve with the altitude? Assuming dry air, we can use equation 1 to express the ratio of temperatures as a function of the pressure and volume. Then, using equation 2, we can replace the volume to keep only the pressure. So we have here express the ratio of temperature, and we keep only the pressure. Finally, equation 4 is obtained by transforming the temperature from Kelvin to Celsius scale. So considering situation 1 at sea level here, 0 meter at altitude, where the temperature is 20 degrees, and the situation 2 at 4,000 meters of altitude, where the pressure is only 613 bars, we can calculate the temperature T2 and we find minus 19 degrees, which implies a gradient of about 10 degrees per kilometers. In the reality, this value is closer to 6 degrees per kilometer because the air is humid and not dry as initially assumed. So heat is supplied by the condensation process. The temperature profile in the atmosphere is illustrated here. Up to the tropopause, that is here the layer making the limit between the troposphere and the stratosphere, it is located at about 11 kilometers above sea level. In this part, the temperature decreases. Then it remains constant in the tropopause, in this limit, that is in fact a thicker layer, and after it increases again. In normal situation, due to this temperature profile, the warm air close to the ground rises because it is lighter than cold air, and these currents entrain pollution produced by human activity. This mixing is enhanced by strong winds close to the ground. But in some cases, when there is no wind and no clouds, the earth cools down at night and cannot warm up enough in the morning with insufficient daytime radiation. As a result, the cold air close to the ground is trapped below a layer of warm air, as illustrated here. And in the absence of wind, no mixing occurs and urban pollution increases. So, we have seen that the pressure evolves with the altitude, but different pressures are also observed on Earth at different stations. Typical weather forecast maps indicate isobars, all these black lines, that are lines of equal pressure, and indicate also areas of high pressure here and low pressure, along with their central pressure value. As a first approximation, we could consider that winds will follow the lines of steepest pressure gradient that are normal to the isobars and go from high to low pressure. So this is what is called the geostrophic model. The force due to the pressure gradient between high and low pressure and the resulting movement can be described by the Euler equations, where vector F represents the external forces per unit mass and dV/dt the fluid acceleration. If we consider a steady movement, the different components of acceleration must be in equilibrium. So the acceleration due to the pressure gradient can be written like this. Because of Earth's rotation, the wind will deviate towards the right in the North Hemisphere due to the Coriolis acceleration. The model of wind resulting from an equilibrium between these two accelerations, the Coriolis acceleration and the pressure gradient, is called geostrophic. As the pressure gradient acceleration runs from high to low pressure cells, the Coriolis acceleration that equilibrates this pressure gradient must point from low to high pressure. The Coriolis acceleration being by definition normal to the velocity, this latter will be tangent to the isobar circles here. So in the North Hemisphere, it will result in a clockwise rotation around high pressure cells and a counterclockwise rotation along low pressure cells. The equatorial area presents high temperatures and thus an ascent of air as sketched here. This air is warm and humid, so it results in low pressures. This area is called the equatorial low pressure belt. This warm air cools down in altitude, leading to intense rain, that is represented here. Then the dry air goes down, forming the subtropical high pressure area around 30-degree latitude, where trade winds travel towards west and westerlies travel towards east. The dry trade winds traveling over the subtropical areas explain the extreme droughts of these regions, where one can find most of the deserts. Over the cold polar regions, heavy cold air goes down, leading to polar high pressure areas. And between the polar and subtropical high pressure zones, the subtropical westerlies meet polar easterlies, leading to an unstable front, as sketched here, where by continuity air rises, like this. This forms the subpolar low pressure zone around 60-degree latitude. This unstable front is the cause of the changing climate in temperate regions like Belgium. In this unstable subpolar low pressure zone, when a mass of warm air meets a mass of cold air, a warm front is formed. The warm air rises above like this the cold air, and at the interface between these two masses of air at different temperature, mixing occurs, and it gives rise to precipitation that can extend over several hundreds of kilometers. We have a cold front when a mass of cold air meets a mass of warm air. The cold air comes and pushes the warm air, plunging below it, and again condensation will occur at the interface due to the mixing, with precipitation occur extending now over a short distance in this case. Finally, an occluded front is formed usually around a low pressure area when a cold front overtakes a warm front, as sketched here. It can lead to the formation of a cyclone or just disappear after precipitation due to the mixing of masses of air at different temperature. The formation of an occluded front is illustrated here. First, the cold air blocks the warm air that was coming from south. Then, due to the Coriolis effect, the two conflicting masses of air start rotating around the low pressure zone that deepens. Then, rising towards the cold air, the warm and humid air cools down, which results in precipitation. The warm air is compressed by the mass of cold air, so wind and rain increase and precipitation occur along both fronts. So we have precipitation along both fronts here. The winds issued from the cold front are the strongest. So the warm air is cut from its source by the cold front, and the warm air rises, forming an occluded front that only exists at higher altitude here. Now isolated, the warm front disappears. The warm air releases its remaining humidity and the storm calms down. A new cycle is ready to start with the two fronts being stable again here. Let us now go back to the formation of rain. We have seen that the key process is condensation. However, in the clouds, the micro droplets of condensate water have a mean diameter of 20 microns, while actual raindrops are much larger, about 0.5 or even 2 millimeter. So how can we explain the growth of these droplets? In fact, for droplets larger than 0.5 millimeter, coalescence is the mechanism of growth. For smaller droplets, the growth results from condensation of water vapor at the surface of some particular droplets, either supercooled droplets, neighbor droplets at different temperatures, or salty droplets. We can now describe the different types of precipitation. In fact, there are three main types of precipitation that can be identified. First, orographic precipitations that occur when a mass of air travels towards a mountain. The air rises, the water vapor condensates, and it rains over the windward slope. The air passing the crest is then dry, like for example the foehn winds that bring a warmer climate to Switzerland, southern Germany, and Austria, as moist winds of the Mediterranean Sea blow just over the Alps. Then, convectional rainfall occur, for example, in equatorial regions, or in summer in our temperate regions, when the warm air accumulates moisture and rises. At a certain point, the moisture content is such that it starts raining heavily. As the temperature is still high, water evaporates again, quite immediately, in such a way that the phenomenon continues until the complete dissipation of the storm, of all the energy of the storm. Finally, the third type is the frontal precipitations that we already discussed. These are also called cyclonic precipitation, and these occur when two masses of air at different temperature meet, and we have the warm front and the cold front. So this ends this lesson about formation of rain, and I hope you enjoyed it. See you next time.